Okay, this is the problem of where a stone is dropped into a well. The stone drops down into the well, hits the water in the well, then the sound of the stone hitting the water travels back up the well, and the person hears this in 3.2 seconds. So the time it took from when they dropped it to when they heard it, the splash is 3.2 seconds. All right. Now we can assume that the velocity of sound, because the sound is going to come up this way, is about 1120 feet per second. Then we're going to say that our time total is going to be equal to our time 1 plus our time 2. Now, what does that mean? Okay, so this side would be distance 1, so the amount of distance that this stone fell is this side. Then as the sound comes up this side, it's distance 2. So it took a certain amount of time for the stone to drop, so we're going to call that time 1. And it took a certain amount of time for the sound to travel up the well. These two times are not going to be the same because obviously that the velocity of sound travels faster than a stone that drops into the well. Okay. Next assumption we're going to say is that G is equal to 32.2 feet per second squared. And then we're also going to solve for T2. So let's see, T2 is going to be equal to 3.2 minus T1. With these simple assumptions, we can figure out how deep this well is without actually measuring it. Other than measuring this, the amount of time it took for it to hear the sound. So that one simple measurement, we can figure out how deep the well is. So the first thing we want to use is kinematic equations when we drop the ball. So we'll use the kinematic equations on the D1 side. So D1 is going to be equal to 1/2 gt squared. And within this equation, there's a velocity in front of this equation. Since we didn't throw the stone down, we actually let it drop on its own. That is actually 0. So this is D1 is equal to 1/2 gt squared. And my D on this side, which would be D2, is going to be equal to my velocity times the time, my velocity of sound times the time it took for it to travel up, which is time 2, and this is time 1 up here. What breaks this problem apart is to realize these two distances are the same. So the 1/2 g t1 squared is going to be equal to my velocity of the sound times t2. The problem with this equation is that there's two different times, and we're not going to be able to solve an equation with two different times. So what we're going to do is we're going to replace T2 with this particular equation. So we're going to have 1/2 GT1 squared equals my velocity of the sound times 3.2 minus T1. Now what we're going to do is distribute the velocity. We're going to have 1/2 GT1 squared. Velocity square, or velocity of the sound, times 3.2 is approximately 3584, and then minus my velocity of the sound times t1. Now we're going to make this thing into a quadratic equation, so we're going to put everything over on the other side. So you have 1/2 gt1 squared. We're going to add this side, so 1 plus the velocity sound times t1. And then we're going to subtract this side, or this amount, which is 3584, and this is going to be equal to 0. We're not quite done yet. Let's put our numbers in. G, which is 32.2 rather, divide that by 2, that's 16.1. T squared plus our velocity of sound is 1120 times time 1. Or just time rather, because we're just going to solve for time 1. And then minus my 3584 equal to 0. This is our quadratic equation. And obviously, to solve a quadratic equation, we're going to use the quadratic formula, which simply states T1 is equal to negative b plus or minus b squared minus 4ac and we take the square root of that thing, and we divide the whole thing by 2a. We're going to hope this square root doesn't have a negative in it. If it does have a negative in it, then we're going to have to deal with imaginary numbers. But so far, I think we're pretty good. So let's plug some numbers in here. My t1 is going to be equal to my negative b, which is negative 1120 plus or minus 1120 squared minus 4 times 16.1 times my negative, very important to bring that negative, 3584. And we're going to take the square root of this thing, and then we're going to divide it by 2 times 16.1. All right, let's go one more step here. T1 is going to be equal to, when we do this, a negative 1120 plus or minus 125, 4400. In this case, because we have multiplication of two negatives, this ends up being plus, which is a good sign. 23080 9.6. We're going to take the square root of that thing. We're going to divide this whole thing by 16.1 times 2, which is 32.2. Alrighty, let's move to the next step. This ends up being t is going to be equal to negative 1120 plus or minus, when we do the square root, we get about 1218.6918. And we're going to divide the whole thing by 32.2. So we should get two answers because we have a negative and a positive here for this particular equation. And lo and behold, we do. So let's look at the first one. This would be as t is equal to negative 1120. We're going to say minus 1218.6918 divided by 32.2. We get t is equal to negative 72.630. Well, there's no such thing as negative time, at least not in this problem. Maybe in Einstein's theories of relativity, maybe, but not in this particular problem. So let's go with our next equation. T1 is going to be equal to negative 1120 plus 1218.6918 divided by 32.2. When we solve this, T1 ends up being 3.0649 seconds. This looks like our solution. Now, if we take this particular time and we put it back into our quadratic equation that we solved earlier, we should get 0, and we do get 0. Now, let's see how this works. So we got our time 1. So time 1 is distance 1 is equal to 1/2 g time 1 squared. So my distance 1 is going to be equal to 16.1 times 3.0649 squared. This is feet per second squared. This is seconds squared. They cancel, ending up with feet. And it comes up to 151.243 feet. All right, and let's see if this works in D2. D2 is equal to the velocity of the sound times T2. Well, how are we going to find T2? Well, we just find T2 simply by saying that 3.2 minus 3.0649, and that comes to approximately 0.135 seconds, around in there. So if we plug this in as being T2, we get D2 is equal to 1120 times 0.135. This is feet per second. This is seconds. Seconds cancel. My distance 2 is going to be exactly 151.243 feet. So that is how you solve this particular problem. This particular problem is the one where you drop a stone into a well. After 3.2 seconds, you hear the sound. And with that particular information, just that information alone, you can draw the conclusion and you can mathematically show that the depth of the well is approximately 151 feet, 0.243 feet.